Right, let's get stuck in. Yeah, so this is what I'm going to talk about. The main core of it is from work that was done a few years ago when I was in Barcelona with Miguel Noasquez, Yelena Goranova, and Antonio Thiem. And since then, there's been a few developments in this line of research, mostly by Annabelle Sainz, Joe Henson, and a few other names, and I'm going to try and review what the main idea is, the background of the idea, and also the progress that's been made since our paper came out. So it's Sunday, so I thought, it's always good to have religious imagery on a Sunday, not knowing I've been already surrounded by quite a bit of it. And I'd like to thank Marcus for the really nice talk, the great discussion, which is going to lead into my talk, which is about quantum theory being somehow a theory of information processing. So that somehow we can derive the structure of quantum theory, Hilbert spaces, measurements, all from information theoretic postulates. And so, as Marcus reviewed, we have these wonderful information theoretic reconstructions of quantum theory, and I just included a random sample here. And all of them seem to have start from different starting points, have different aspects to them, they use different postulates. It's very nice you have all these different points of view on the reconstruction of quantum theory. And they all start from some broad operational framework, the generalized probabilistic framework. Maybe you have operational probabilistic theories, the circuit-based approach. You bring in these principles and you recover finite dimensional quantum theory. And then once we have finite dimensional quantum theory, we have all the stuff that we love about quantum theory, or stuff that baffles us. So non-locality, no broadcasting, computational speed-up, contextuality, key expansion. I work mostly in quantum information, so I have my personal preferences amongst those things that I find nice about quantum theory. But you could just skip this intermediate step of going to recovering the full structure of Hilbert space quantum theory to get to these interesting aspects of quantum theory. You could just skip this step completely and just start from the broad framework, bring in some minimal principles or minimal constraints, and then try and recover aspects of quantum theory directly. So there's quite a few papers in this line of research. And then the natural question is, well, maybe you don't like the structure that's brought in your broad operational theory, your framework. Maybe it's already making too many assumptions. Maybe it's not really getting to the heart of information theory. So you can start asking, well, what is the minimal background structure required to start recovering these properties of quantum mechanics? So in particular, this talk will start from just black boxes, very simple structure, and ask whether we can get down to quantum non-locality from this very minimal structure. And the broader historical context of this was really in the 90s, before these recent reconstructions came in. So we know quantum theory is incompatible with a local realistic explanation. However, it does not permit faster-than-light communication, so Shimony, as I'm sure we all know, called this the peaceful coexistence of quantum mechanics and special relativity. And then, inspired by this, Shimony and Howard have asked, well, is quantum theory really the only possible theory permitting both non-locality and non-superluminal signal? Is this the only theory that really resolves, is happy with this tension, let's say? And then, as Marcus said, Popescu and Braulik said that there is an imaginary device that we can conceive of called the Popescu-Braulik box that does not permit superluminal signaling, but gives non-locality that is incompatible with quantum mechanics. So then, if that principle of no signaling does not recover quantum non-locality, if there are other possible theories out there compatible with special relativity, then is there another fundamental principle or a set of principles not couched in the language of quantum theory that singles out quantum non-locality? And over the past 17 years or so, there have been many proposals for information theoretic and physical principles that recovered some of the quantum predictions, some of the more famous quantum predictions, but didn't really recover all of them. And the main point of this talk is that the main point of our work was to actually come along with a set of correlations that made good sense, was a very sensible set of correlations, and we called it the almost quantum correlations that I hope, for reasons that will become clear later, that really satisfied all those proposed principles that were outlined in the subsequent years. Sorry, in the years before. And so we were using this to argue that this set is really an obstruction to recovering quantum non-locality. So we were pretty pessimistic about this program of taking this minimal framework and trying to get back to quantum non-locality. But the step turned out to be actually quite interesting, in that it has a nice description in terms of a very simple, elegant principle, and also it has connections to the history's approach of quantum gravity and has other approaches, has other connections to themes in quantum information. So whilst the outcome was kind of negative, we thought that there was actually some merit to studying this set of correlations. So the plan of attack for this talk is to review this minimal framework in which we're considering non-locality, then describe all the kind of physical and informational theoretic principles that were proposed within this framework. I won't go into detail about all of them, I'll just give a review of some of my favourites. And then I'll get on to defining this set of almost quantum correlations. And then, since this is a philosophy conference, I thought I'd include some Latin. And then, so I'm going to ask, where's next? I even italicized it. Yes, good. So what I'm going to do now is I'm just going to review the basic framework in which we're thinking of these correlations. So it's essentially a Bell test. So we have some local agents that have some black boxes in their laboratory, and they've got some classical data which they can plug into these black boxes and receive some data out. Because these are black boxes, we're not really breaking up the operations into constituent parts. We're not directly studying the preparation devices and measurement devices. For us, these are just black boxes that produce some classical data from which we can generate statistics. And the local agents are not really restricted in how they obtain the classical data. They have some local method for generating classical inputs that they plug into the box, and then for simplicity we just say that they obtain an output immediately from these boxes after plugging in the input. So this is just a simplicity assumption. So the agents don't have to wait around after they produce the input to receive the output. And then the objects of interest are these conditional probability distributions of outputs given inputs, which we'll just call correlations. So these things on the right here. So I have 3 boxes here, but you can imagine n boxes, and you have n local agents who can generate this data. They can talk to each other to then generate this data. And aside from the fact that this is a Bell setup, and the Bell's theorem is obviously of great foundational importance, why care about such a limited framework? I mean, the agents don't even have access to the systems that they can prepare, right? They just have these black boxes. Well, one reason why I really like it is because it's so minimal and simple that even I can understand it. So I can actually follow what's going on, and I don't have a very sophisticated mind, so it's great. I like that you just plug things in and get things out. And a lot of the motivation for this, and some of the personal motivation, is coming from quantum information processing. That you can think of a cryptographic scenario where agents' devices are
are manufactured somewhere else. They then buy these devices, they come into the laboratory, and they only have access to classical data that they can plug into the boxes and get classical data out. But still, you want to use these devices for some cryptographic task. So then the first principle is the no signaling principle, where essentially that just means mathematically that the marginals are well defined. If I basically sum out of the outcomes of one party, then I recover marginal statistics for the other parties. So, for example, I put that expression up there. And this does put a non-trivial constraint on the correlations allowed between these agents. And if I just view these correlations as just entries of a vector, it just puts some linear constraints on this vector that lives in a real vector space. So then I can just come up with, as Marcus mentioned, the non-signaling polytope, or the banana world polytope, which is just this polytope living in a real vector space, which is defined by these linear constraints. And these are just a hyperplane in this real vector space. And then the intersection of these, the half spaces, is then the non-signaling polytope. So clearly local correlations live inside this space. Whereas we think of the local correlations are those that are associated with some distributed classical instructions, and then no hidden signaling between these classical devices. So then we have some hidden instructions described by lambda, some distribution over lambda, and then the outcomes produced in each laboratory are just dependent on the inputs and then lambda itself. And then this forms a convex polytope within the non-signaling polytope. And then the facets of this polytope are just the Bell inequalities. They are Bell inequalities. And then we know by Bell's theorem that local measurements on multipartite quantum states violate these Bell inequalities, so we have to associate the set of quantum probability distributions with some set living outside the local polytope. And then we know that these quantum correlations do not saturate the whole of the non-signaling polytope. There are vertices of it which gives stronger non-locality than quantum. So a PR box, schematically, it's just some vertex of this non-signaling polytope. So, this was pointed out by Calvin and Saracen quite a number of years before, but unfortunately I think it gets overlooked. So I put it there for completeness. And so, for completeness, I've just got the Popescu-Raulich non-local box here. I have two parties, and when their inputs are both not equal to 1, they have perfect correlation. And when x equals y equals 1, they have perfect anti-correlation. But then the marginals are completely random. So you plug that into the CHSH inequality, you find that that gives you a value of 4, which surpasses Saracens bound 2√2. Good. Okay, just a word on terminology. I'm going to be a bit sloppy. So geometrically, these sets are defined with respect to particular scenarios, so particular numbers of inputs and outputs. And I'll be sloppy and just refer to the local quantum non-signaling sets of correlations as just respective sets for a given choice of inputs and outputs. So this is maybe analogous to the Hilbert space dimension or system types in general theories. Okay, and I should really formally outline what the set of quantum correlations is if we're going to recover it. So it should be those correlations resulting from local measurements on a quantum state. However, there are two main possibilities for this definition. Often one gets put up in talks, but there are actually two possibilities. The first one is that you just consider the tensor product of a bunch of Hilbert spaces for each party, and then you have some measurements applied on systems in each of those respective Hilbert spaces. So you just have a tensor product of measurements there with respect to some state. The second possibility is that you define measurements such that they, in the bipartite case, commute with each other. Or in the multipartite case, you just take any permutation of these operators and you get the same statistics. So you get this kind of generalization and commutation. So I commute these operators and I get back essentially the same object. Now for the finite dimensional Hilbert spaces, these definitions actually are equivalent. But in the infinite dimensional case, it gets extremely complicated. This is relevant to something called Saracens Problem. I mean, I think it was his problem because he thought it was true in the infinite dimensional case, but it turned out to be not quite as simple as that. And there's very recent work which is trying to basically clarify the relation between these two definitions of the quantum set in the infinite dimensional case. So for instance, one result is, if we take definition 1 as our definition of quantum correlations, that deciding whether correlations are quantum by this definition is actually it's an undecidable problem. You kind of have to, I give you some conditional probabilities and you have to say, does there exist a quantum realization of that thing? Well, you can just loop through all possible Hilbert space dimensions and look for those measurements and states to see if it realizes it. But fortunately, this general problem, you can prove it to be undecidable. And so for convenience, we'll just consider the definition to be the more general definition of the commuting operators. And things are a bit simpler in the case of defining the correlations in terms of commuting operators, that we actually have some computational tricks to get back down to this set, using an infinite hierarchy of semi-definite programs which actually converge to this set in an appropriate limit, which is this Navasquez-Peronia-Thien hierarchy. So the whole point here is, like, for each level in this hierarchy, that there is an efficient test for whether your correlations are in that set or not. So it's a nice numerical trick. However, for the set Q, defined with respect to these commuting measurements, we don't know if deciding set membership is actually decidable or not. So this is still an open question. So, okay, given that there are definitions of the quantum set, and I've just outlined them, and that's all great, we go back to our original question: is there a fundamental principle or a set of principles which are not couched in quantum theory that singles out quantum non-locality? Well, first you might say, well, the previous slide told me deciding whether something is quantum is extremely hard, so is this just a failed endeavour from the outset, right? If we can't decide whether a distribution is inside the set or not, then I have some principle which bounds my correlations. How do I then decide whether those correlations are then realisable in quantum theory? And I would say, yeah, that's a good technical challenge, but it's interesting to ask, well, given that this is a problem, let's still come up with information principles and see what that buys us. And we can also just ask fun, simpler questions like, for the CHSH inequality, can one recover Saracens bound given these principles? So now I want to delve into the proposed principles in the literature. So here's an overview of the principles out there. I'll mention a few of them, but not all of them. If people want to know what some of them are, and I've not described them, just ask me later. And you can see there was a real flurry of activity in 2009, where it seemed like a very promising direction of research at the time. And then it's kind of, after 2013, it's dried up somewhat, so I don't know if this dates my research or not, but who knows. So I've already mentioned the no signaling principle, and that doesn't quite give us the quantum non-locality, but there is another principle that you can come up with, which is the idea of closure under wirings. So this is a kind of very operational principle you can come up with. So I have the local agents, instead of just receiving one black box, they can receive multiple black boxes. They can just wait before they plug things in. They can receive multiple black boxes from their from agents. And each black box is associated with its own probability distribution, its own set of correlations. And then we ask that the set of correlations is stable under composition of black boxes. So I can just have some general set of inputs and outputs, and then I just treat that whole thing as a big black box, and I ask that it's still in the set after I've done that coarse grading. And then furthermore, the agents can actually begin to locally wire together their boxes according to some circuit, which is a technicality, to generate a new distribution. So they have some P1, which is in some set T, P2, which is in the same set, and P3 again. And then they have some process of plugging these classical inputs into, classical outputs into inputs and inputs into outputs, just as long as you don't get cycles. And this whole process is described by lambda, and then you ask, after applying lambda to these distributions, is that still in T? And then if it is, then the set is closed. And also agents can post-select on measurement outcomes, which is, okay, I want to generate some correlations conditioned on certain outputs. So if I get the output A1 for input X1, given I condition on that event, and I just generate some correlations conditioned on it. And this is a pretty useful principle, because we already know that certain sets, such as the quantum local non-signaling set, are closed in this manner. So that means the principles of closure under wirings and non-signaling do not actually recover quantum non-locality, because the whole point was that the non-signaling set is also closed under these operations. But at least they give us nice baseline principles for our framework, such that we can postulate further principles and then use these ones in conjunction to end up with the sensible correlations. Good. Okay, the next one I want to talk about is one that I think really got this whole search for information theoretic principles for quantum non-locality, got that whole approach going. So the general approach here is of communication tasks, where, okay, we have our boxes that satisfy no signaling, and then we allow the agents to talk to each other so that they can carry out some task. So that the only permitted signaling is that which is done by the local agents. And then we ask, given these resources and communication, can they achieve some task, given these resources? Yeah. So the first one is a communication complexity task. Which, okay, I know we're getting into engineering here, but just bear with me. I think it's quite a nice task. So two parties each get some input string, and they're allowed to classically communicate after they get these strings from one party to the other, from Alice to Bob. And then Bob's goal is to output a function, a Boolean function, dependent on both inputs. And then we put a constraint on the amount of communication that Alice can send to Bob. We say that this communication is constant, it's independent of the input size, independent of n. And then for any function, if this task is trivial, then the probability of winning at this game, of outputting that function, should be bounded away from half by some constant. And for the case of quantum theory, there is a function, which is the inner product function, which is basically the pairwise just inner product for these two vectors, where this is impossible. You cannot achieve this with some probability bounded away by half, by a constant, given only a constant amount of communication. So it turns out that in the quantum case, the number of bits you have to send is lower bounded by n. But then Wim van Dam, in his PhD thesis that ended up in the archive 5 years later, showed that PR boxes can do this deterministically. They can achieve this function deterministically, given just one bit of communication. And in fact, they can do any Boolean function using one bit of communication. Constant amount of communication. Deterministically, yeah. So then the question was, okay, PR boxes are ruled out by this. Can we have some other set of correlations which are a bit noisier, which can be ruled out by this principle. So Gilles and a few others extended this to a probabilistic family of protocols that got very close to recovering Saracens bound, but didn't quite get there. In fact, it's still an open problem whether you can recover Saracens bound using this principle. Good, okay, so that was non-trivial communication complexity. The next one, which is a communication task, is information causality. And so the broad principle here is that the information gain that Bob can reach about previously unknown data to him data set of Alice by using all of its local resources and m classical bits communicated by Alice is at most m bits. Okay. And then the idea is there that you have this task and you have some communication m, but the only information that's acquired by one party is this information m. So in this paper they thought about a very specific task where now Bob has to output a specific element of Alice's input, given communication from Alice to Bob only. And this is quantified by the mutual information between Bob's output and an element of Alice's input, given a particular choice of input for Bob. Great. So information causality then bounds this this number by m. Great, and starting from this constraint, you can show that quantum correlations satisfy this principle. So this is always satisfied for quantum systems. However, PR boxes violate this principle. So given m bits of communication, using PR boxes, basically Bob can learn what he wants. And then using a specific family of protocols, you can derive Saracens bound for the CHS inequality using this principle. Okay, so these were in the language of communication tasks. And then the next one I want to talk about is something maybe a bit more physical. So in macroscopic locality is one where is a principle where you want to recover some macroscopic limit of the experiment, and then say that there's some classical explanation for that macroscopic limit. So the idea is if agents obtain n copies of the same boxes, and then they coarse grain the data that they receive from these boxes, and they turn it into something called intensities, then the infinite limit of n, the statistic should have a local explanation, should have a classical explanation. So here I take many copies of these boxes, and I take the data out, and then in my measurement devices, I just basically get rid of some of the information about what events occurred. I just have some resolution on my detectors that only can measure fluctuations about a mean of about square root of n. So once I coarse grain the measurement outcomes, I then look at the infinite limit. I say there's a local explanation. And it turns out that quantum correlations, again, satisfy this principle. You take a bunch of quantum systems, you coarse grain the outputs of these devices, and then you take the infinite limit and you find there is always a local explanation. But PR boxes, again, violate this principle, and it is possible, again, to derive the Saracen bound from this principle. However, interestingly, this is the first time where it's provably shown that you cannot retrieve the set of quantum correlations using this principle. They recover some level in this MPA hierarchy that I mentioned. Okay, so I've outlined some of these principles. Again, if you're interested in the other two that I've not mentioned, just ask me afterwards. So yeah, there was a period of years where people were coming up principles, recovering Saracens bound, and ruling out PR boxes. This was a very fun game that was played, and I quite liked it. And in some cases, we had that we could provably not recover the set of quantum correlations. So what one could carry on doing in this fashion is just keep coming up with more principles that recover the quantum bounds for Bell inequalities, or you use the principles you already have to recover quantum bounds on other Bell inequalities, or you could just come along and say, well, here is a set of correlations that satisfies all of these principles. And that's exactly what we did. And because it's the almost quantum correlations, the quantum correlations are our starting point. So if we took this definition that we had earlier, that probabilities are due to commuting measurements, or in general, you think about these permutations for the n-party case, we can actually relax this set of constraints and say there just exists some quantum state where the probabilities I obtain are just the expectation of some operators on this state. And when I permute the operators that act on this quantum state, I get the same product of operators. So this is not the most general thing of just asking for some form of commutation. This is just saying for that particular state, I can replace this permutation of operators with another permutation of operators. Okay, and then the set of correlations derived from this is the set of almost quantum correlations that we proposed. So one kind of working way of thinking about this is to think of it as like a fine-tuned quantum experiment, that there exists a particular state that's such that I can have potentially non-local operators acting across several sites that actually give the appearance of commuting. So that means that the resulting correlations satisfy the no signaling principle. But the important thing is, because we just have this existential quantifier instead of some universal quantifier, we know that the set is larger than the quantum set. It can be potentially larger than the quantum set, so we prove analytically that this is true in the paper. And we showed that this set is actually exactly equivalent to one of these levels in this hierarchy of semi-definite programs. So that's quite nice that you have some physical definition of the set and it corresponds to some elements of the program.
You mean properly loaded?
Sorry?
You mean properly loaded?
Yeah, properly larger, yeah. Okay, now then once we have this set, which is larger than the quantum set, we can begin to ask whether it satisfies all of our principles. Okay, I just said it satisfies no signaling. It also satisfies closure under wirings. So you can play this trick where you take multiple copies of a box, you plug inputs and outputs, you do it as long as you avoid cycles, and then you generate something new, and you ask, is that in the almost quantum set? And it turns out that is true. It also satisfies the principle of non-trivial communication complexity. You can show that these sets of correlations to compute some particular Boolean function, they cannot be done trivially, as in the case of PR boxes. And it satisfied all the other principles. The only one that's left, which we don't know analytically that it satisfies, is information causality. However, we do have really good numerical evidence that it is satisfied here, but it's not the same as analytical evidence, sure. Okay. So we have a really good candidate set of super quantum correlations that satisfy sensible properties and all but one of the proposed principles. And the nice thing about this, because it's in this level of this hierarchy, it actually, you can efficiently decide whether a distribution is in this set, as opposed to in the quantum case where it's a potentially undecidable problem. So maybe like in physics, you don't like the fact that nature maybe is undecidable, maybe you only ever want decidable problems, so it's a good reason to prefer this set. But more practically in quantum information, it's nice to have something decidable as opposed to undecidable. But the whole point of the set when we were coming up with it was, okay, here's a major obstacle in any attempt to recover quantum non-locality from fundamental principles. Great, okay, you can define this thing and you show that it's an obstruction. However, it's like if I want to take this thing seriously, it's not so nice that it's defined in using quantum mechanical language. It uses Hilbert spaces, it uses rays in Hilbert space and projectors. It's not so satisfying. So then the question is, well, can this set itself be recovered from a single principle? And it can.
And a very nice result shown by Belen Science and Joe Henson in 2015. A principle called Macroscopic Non Contextuality, which is a generalization of macroscopic locality, can recover this set exactly. And they use this hypergraph approach for studying contextuality, which basically, to give a kind of a quick overview of it, you have the idea that you have experimental events, and then events exist in some context, and we can represent events in context by a hypergraph. And then, so each of these hyperedges says that this is a possible context. Okay, and given a whole bunch of events, there are multiple hyperedges between them. And so this adds in more constraints than just between local agents and non-signaling. It could allow a form of one-way signaling that, given a particular event, Bob's activities can be conditioned on that event. Okay, and then you come along, you take this definition of hypergraph contextuality, and then you apply the same coarse grading to events, as in the macroscopic locality case. And then you say that the intensities I obtain in my lab in some infinite limit can be described by a non-contextual hidden variable model. And then this principle here recovers the almost constant case. So that's very nice. It's something about agents in the infinite limit, when things become macroscopic, recovers this set of correlations exactly. And then, I'm no expert on the histories approach to quantum gravity, but there is a very nice paper by Faye Dowker, Joe Henson, and Petrus Walden that shows a very direct connection between this set of almost quantum correlations and something they're attempting in the histories approach. So, to give, like I said, I'm not an expert, but I give a broad strokes outline of histories, that we have some set omega of space-time histories, and the aim is to assign a measure on the algebra of events associated with these histories, and then decoherent histories, or consistent histories, aims to recover observed probabilities for observations made by agents within this set, so it's internal to the theory. And the idea is you want to recover probabilities that you observe within these histories. So if we just restrict our attention to subalgebras of events that give probabilities, then we want to define something called the decoherence functional, which satisfies a bunch of properties. So this is very much in line with the quantum measure approach of Raphael's law. Okay, and so taking this definition of this measure, if we just restrict ourselves to a Bell test, so given just the statistics from a Bell test, if when restricted to measurements in a Bell scenario that then define some algebra for us, the decoherence functional reproduces the observed statistics and satisfies some property called strong positivity. Then we get a set of observed statistics called SPJQM, Spijacum. Then when we take this set and take the closure of this set under wirings, we get exactly the almost quantum set again. So starting from a very different motivation, one line of research converges upon another. So I quite like this, and it's got nice connections to this hierarchy of interference that Sorkin has talked about. Okay, so in the time I've got left, I'd like to talk about where this kind of line of research is heading, and where to go next. Oops, okay. So there are several directions, like given this result, where do you go from it? Okay, it's got a nice characterization, nice connections to other aspects of quantum foundations. However, it's still an obstruction to characterizing the set of quantum non-local correlations from information principles. So you can just say, well, I'm going to find some better principles, perhaps ones that rule out the set of quantum correlations. And we haven't entirely killed this option. So, and some people are pursuing this. Yeah, but I'm not quite sure what's going on.
So in a paper by Lopez, Rosa, and Cabello, they conjecture that something saturates the exclusivity principle, which actually is the local orthogonality principle, and that therefore this local orthogonality principle that I mentioned on the slide a while back, which is one of these principles that almost quantum satisfies. And then it's conjectured that somehow the reason why the almost quantum set is non-physical is because it violates this principle, the exclusivity principle, that we know this set satisfies. So I'm not really sure what's going on there. So there may be some other principle out there called the exclusivity principle, which does violate almost quantum, but I'm not quite sure. And then I got this email a month ago that was quite nice, that said, "Hi, my collaborator and I enjoyed the paper Almost Quantum Correlations, and then y'all give numerical that probably gives a geographical location to the person who wrote the email. Y'all give numerical evidence but not a rigorous proof that almost quantum correlation satisfies information causality." Okay, that's true. And they have an idea for how we might prove rigorously that there exists super quantum correlations, but not necessarily almost quantum set, that satisfy information causality. And then could you please confirm that would be a new result? So someone's thinking about this still, and that's great. So I don't think the progress in this line has slowed down. Someone's actually thinking about it and pursuing it, which I think is wonderful. And then some people are saying things which are confusing. Good. So a second direction is, well, okay, the fact that the almost quantum set satisfies these principles might just be a quirk of the framework we're starting out with. I mean, we could just move beyond this very limiting framework of Bell tests and black boxes. As I said earlier, we have no controls over the preparations of systems. So one option is, well, we could just move to more complicated networks of agents, move beyond the Bell test, but still have like them using black boxes. And then this is all good and well motivated cryptographically if we want to think about these black boxes being prepared by some agent somewhere. But it doesn't quite capture like certain information processing tasks that I care about, such as efficient computation. In efficient computation, you want some certificate that your devices are efficiently prepared by some system. And then, certainly an approach I like a lot is you just consider generalized probabilistic theories, which have a lot more structure and are very powerful for saying very interesting things. And give a very nice broad framework of the kinds of questions you can ask. And then the third thing is, well, the fact that this set has very nice properties, you just embrace this set and you say, okay, it's really nice, it has connections to other things, it has a very efficient characterization. Maybe this is potentially something new that we can test in the laboratory. So why not come up with a sensible toy theory that reproduces the set of almost quantum correlations? I mean, there is a way of reproducing this set, but it will involve like hidden signaling on quantum devices, but it's not so great. And the fact that there is a clear principle picking it out and membership is decidable, these are very nice properties that should really make us think that maybe there is a sensible theory out there for this thing. And then we should try and use the framework of generalized probabilistic theories to describe an operational non-quantum theory that is somehow a foil to the quantum theory. So progress in this direction actually seems quite difficult, and you can come up with some no-go results, which I can go to. I can discuss briefly if people are interested. There's some work by some of my collaborators in preparation. I'm not involved in it, so that's why I can only discuss it briefly. Okay, so to just quickly summarize, the task of recovering quantum non-locality from various principles in such a basic framework is really a big ask, but it's quite nice that some ingenious progress has been made. That's what I quite like about this. But unfortunately, the set of almost quantum correlations is an obstacle to this task. So maybe we don't get a nice reconstruction that we do in the case of the generalized probabilistic theories, and it's really like a failed endeavor.
However, this it has such a nice characterization and connections to other aspects of quantum foundations that I think perhaps maybe it is leading somewhere, and it's interesting to pursue as some alternative to quantum theory. However, turning it into some fully formed theory that we can think about testing or building devices seems very problematic. Okay, I guess I wanted to introduce some broader remarks, but I think my first point was certainly discussed a lot and addressed within Marcus' talk. But just to add that these information theoretic principles, they're just imposing constraints on local agents in this very basic framework. Maybe it is really just not saying anything about quantum theory. I mean, a priori, these communication tasks have nothing to do with physical properties of systems, yet they somehow recover facts about quantum theory. So it could be that recovering Saracens bound is just pure coincidence. It's as good as numerology. I have two ideas and somehow they converge upon the same fact, but am I really saying something fundamental about quantum theory? However, in this direction for me, a full information theoretic axiomatization of quantum theory is certainly more compelling evidence along this direction, but information principles should be saying something. And then, whilst I was preparing this talk, I went back and had a look at some of the original papers in the 90s by Harinov, Shimoni, and Pesco and Rawlik. So, Harinov, when he was referring to non-locality, was referring both to Bell non-locality and the AB effect, when he was describing the broad phenomenon of non-locality. And then saying that is in tension with relativity. So is it somehow that quantum theory is the only theory which, where this can happen, that some dynamic non-locality as well as kinematic non-locality is compatible with relativity? So our black box approach is really only addressing Bell non-locality, right? So it's kind of leaving out the AB effect. And then my question is really, well, is our black box approach really addressing whatever this perceived tension is between special relativity and quantum mechanics? And is it going to be satisfactory to people who are really interested in this? Okay, and those are my final remarks. And so I'll just conclude with the same religious imagery that instead of Hilbert spaces, maybe we should think about what was given to us was the almost quantum set. Okay, thanks.